working with free manifolds, it was this idea that something else could be set in a different way by means of algebraic structures without the so-called invariants or quantum invariants. There were before the classical invariants, which are quite old, going back to Alexander, or let's say maybe it was just to Poincaré. But the idea to put in classical invariants was to find invariants you are able to compute in a very explicit way, and also to compare, which is a different thing. All finitely represented groups arise as fundamental groups of four manifolds, even symplectic ones. Nevertheless, there are just a part of them which occur as free manifold groups, and we know that the problem of deciding whether two free manifold groups are isomorphic, let's say the problem to say that a free manifold group is trivial was in principle solved, but the algorithm is extremely complex, extremely complicated. And the general problem, I'm not sure was completely done. And yeah. So in some sense, we'd like to have invariants like numbers or polynomials or whatever algebraic invariants, which are much better. So one idea was to put some structure like algebraic structures, which would be higher order structures. Typical, you're going to see a lot of acronyms here. These are the so-called modular tensor categories, but I also like something coming out from physics, from formal field theory. Now you have the free manifolds, and you have kind of pairing. These pairing are giving you numbers or polynomials. Let's put numbers to be easier. Now it's quite clear what the meaning of such construction, starting from a probably complicated structure. You put two free manifolds up here. If you get different numbers, the manifolds are different. And you solve it in an explicit way the homeomorphism problem. Of course, you solve this if you have enough algebraic structures like that, and if you know things about how good are these algebraic structures to detect free manifolds. So in some sense, of course, if you want to construct Finn invariants. Okay, so this is one of the aim of the topological quantum field theory, to study such kind of invariants, to explain how they arrive, what information is recorded into these numbers. And one problem of the theory is that you actually get not one, but you get a lot of such algebraic structures. You get plenty, and you have to organize them and to analyze them into higher order structures, even more complicated. So one remark I want to do, just to have a better idea of the complexity of the free manifold, is that the GSG decomposition, I said it existed and just cut out along Torah, is not exactly, just not to say too many fake theorems. GSG decomposition is not exactly, it's almost not exactly the geometric one. But in most cases it works, but not in all of them, just to know that. For instance, you might have GSG decomposition pieces. You can have GSG pieces without finite volume. Geometry. geometric structure. I think that the simplest one is the mapping torus and phi, and also map of the torus, in which case you have a solved structure, but the GSG decomposition is cutting you once more along the internal torus, and you don't get a final geometry. So the description is not perfect. The correspondence between geometry and GSG decomposition, but it's almost. Also, closed free manifolds have an unique geometry. The closed free manifolds have a unique geometry. If it has the hyperbolic geometry, it cannot have, it cannot have. But those of finite volume and with boundary, they might have two. And when I define the geometry, I just put them up here. There are a lot of other geometries. There are a lot of other geometries, but you don't have a finite volume. You don't have lattices in them. The associated Lie group is not unimodular. So these are not usually considered as geometry. Okay, so let me state. Yeah.
If there is a boundary, the geometry is not unique.
It might have two. There are some peculiarities. Also, so let me give you the final example. So what about the pi 1? The pi 1 is finite. So the pi 1 of the free manifold is finite. Okay, so here you have S3, you have the geometry S3, and these are the quotients by S3. So here the free manifolds are just geometric. Geometric means these are pieces and closed. The pi 1 then is infinite. This is the next step, and it is infinite virtually simple. Virtually cyclic, but infinite. So it is not in case 1. So the geometry is the next one. It's S2 plus R. Now the next step. Pi 1 is virtually abelian, not virtually cyclic. Virtually abelian, not virtually cyclic. Okay, so this is A3. The next step is pi 1 is virtually important. And of course not virtually abelian. Then you get the geometry is near. Pi 1 is virtually solvable, not virtually nilpotent. The geometry is solved. Pi 1 is so pi 1 is not virtually solvable, and there is a Z, a normal subgroup of pi 1. then the geometry is alright. Yeah, the geometry could be either of H2 cross R or PSL2R2. I don't remember exactly how to distinguish between them, but yeah, it's probably not important. And this is the first case where you can get compact and non-compact such free manifolds. And 7, well, the last case is phi 1 does not contain V as a normal subgroup, then it is hyperwide. So in some sense, this is saying you what you can expect from the PC. You get better and better, higher and higher complexity of the phi 1, and this is saying you exactly which is the geometry which appears. Okay, so this was a bit in a rush. I didn't meant to say that free manifold topology is dead. There were recently very nice results, as I said, by Jan Nagel and also by Karl Markovic, for instance. Let me just take a theorem to make the things to see the flavor. So I'm taking always a closed, irreducible, free manifold, infinite pi 1. Infinite pi 1 makes them, as I said, spherical. So then what Nagel proved is that there exists a finite cover. So if I'm just saying so here is M, I need to find over M over M. Let's say H1 of M with R coefficient is not 0. So you can take also N to be a fiber bond. The surface bundle of surface bundle over this one. In some sense, this is saying that free manifolds in the most generic case, the most general and maybe the most interesting, up to a finite cover are obtained from a circle by taking a surface sigma of genus G and taking an element of the diffeomorphism group of sigma G and identify sigma G cross 0, 1. You identify a point of the form x0 with a point of the form phi of x1. Okay, this is a suspension of a diffeomorphism, and basically all free manifolds appear like that. And this is the way I'd like to think about free manifolds as obtained from elements of from the diffeomorphism group of surfaces. So, and this is the theorem due to Hegel, as I said, building wise. And also this is related to this one. In the there is some G at least 2 and some embedding of fundamental group of surface of genus G into fundamental group of M. So this is kind of Markov. So So now I'm gonna stop saying things about the precise structure of free manifolds. I think it is enough for having a rough comprehension of this object. And now I'm gonna say a few words in the last, I don't know, 10 or 15 minutes. 5 minutes. 5 minutes. Okay. 5 minutes. I'm gonna say just a few words about what means a TQFT. It's a long story starting from it's the quantum, the Q coming out from here, which makes them more interesting and related to new work, to quantum topology. So yeah, maybe next time I'm gonna say more about the history from the Jones polynomial and so on. The idea is that this is a function. A function from what? Well, from one category. One category I would like to see is the coordinates of surfaces. So objects are surfaces, and morphisms between surfaces are coordinates bounding that surface. So let's say coordinates in dimension 2, and where do we want to arrive is in the category of vector spaces. So vector spaces are the object, and homomorphisms between vector spaces are the homomorphisms into that category. So to make a picture, to a surface you associate a vector space. To the average surface, so here is sigma 1, sigma 2. So you have a vector space W of sigma 1, W of sigma 2. The coordinates between them is giving you M, is giving you a map between them. Okay, and that's very easy. Would like to add the adjective topological, so we want all these things to be topological invariant, meaning that you have two homeomorphic surfaces, then you get two homeomorphic vector spaces. You have two homeomorphic free manifolds which are bounding the same surfaces, then you get out of that. Then you get again a morphism which does not depend but only on the homomorphic T. But this is somewhat tricky because, what means exactly? Yeah, what means exactly to have such a structure if you want to add more axioms like gluing, meaning that here you could compose these coordinates, M1 here you put M1, 2, and you want to get by functionality the composition up here to be exactly the result of here is sigma 2, the same surface, sigma 3, and here you want to find something which explains what the functionality. So here you have to take into account at first the possible gluings in the topological realm, and then to make this more clear. So there is a lot of hidden structures. The first is the gluing, and second is the so-called quantum axiom, saying that it should be a relation between different, if I'm taking a surface which is not connected, now is sigma G union sigma H, then W of these two is the tensor product of W of the surface sigma G, product W of the surface sigma G. So this is one axiom which has not been encountered before in its present form. And well, in general, one adds one more axiom saying that there is an extra surface, namely the surface without the empty surface. And traditionally, or we just put the space associated to it is the one-dimensional vector space over the complex number. So, all examples occurring until now are naturally coming with a complex structure, and now there are some other cases in characteristic P and so on, which, so this is what
You don't need any Hermitian structure on your vector space?
No, a priori you don't.
Okay.
From now you don't.
So there is no relation between...
After a while you could see that sometimes you could put a Hermitian structure, and it is not always Hermitian, it might be pseudo-Hermitian and so on, so you could add some more structure. But for the moment, all these things are very vague, because what means gluing? This is what I said. And actually, a lot of things are hidden here. So now, the other two are very clear what means. And then also the topological things, that means that here, if you have closed surfaces, the W, it depends only on the genus. So you have one genus, one vector space. And then after that, you have to define carefully what means gluing and so on. This could be done at this formal level, but this also can be done in another level, at the algebraic structure called modular tensor category, when this come out in a more direct and more explicit way. So this is the aim, to construct something like that. What would be interesting? But because if you take a closed free manifold, that means you can see it as a coordinate from the empty set to the empty set. Now that means that such a thing is giving you a number which is necessarily invariant. So that means invariant of free manifold. It's a bit the other way around, but it's a very funny object. Okay, thank you very much.
Some other questions? Thank you. The next talk is 2 o'clock in the afternoon.
Almost,